Hello? Okay, okay. Fine. So, good afternoon to all of you. So, I am Professor C. Nagaraju, Department of Computer Science and Engineering, OSR Engineering College of Yogavamana University, Pradipur. So, today I am going to discuss about LR0 and SLR1 parsers. So, that means top-down parsers. So, today's contents are Introduction to Bottom-up parsers, LR0 parser, example problem, great questions on LR0 problems, LR1 parser, example problem, gate questions and solutions. So what do you mean by bottom up parser? The construction of parse tree for any given input string beginning at the bottom and working toward the root is called bottom up parsers. The construction of parse tree for any given input string beginning at the bottom and working towards the root is called bottom up parsers. So in the previous session already I explained a top down parsers. So in the top down parsers, so that is the string, so that is a construction of parse tree or verification of the string start with the root node and it moves up to leaves nodes. But here is the top-down parser is, so that is reverse to top-down approach. So here is in the bottom-up approach. So bottom-up approach, it start with the leaves and it move up to the root node. So this is the top-down parser. So for example, you see that it is a grammar, it is a context, so that is the context-free grammar. And in this case, suppose you see that string I had taken, suppose ID star ID. So first one is in the bottom of parser. So first we can start at the leaves node. So in the leaves node, first we are taking the instruction ID into ID. So after that, so suppose here is ID, you see that ID is the leaf node always. So that means here is ID. So that is ID is replacing with its parent node F. Its parent node F. For example, you see that. So in this expression, so F tends to so E within the bracket R ID. So then here is in these two productions. So we are taking so F is equal to ID. So that's why here is ID is replaced with F. So after that, again you see that F is the, so that is the child of T. F is the child of T. So then here is F is replaced with T. F is replaced with T. That is a non-terminal. F is replaced with T. So then after that, so again you see that T. So that is here is a T. So is replaced with the first production T star F. So because you have to get the, so that is the string. So that means the T is replaced with so the T star F. So here is in this F, again you can see that. So that is the T star F. Again you take F. So that is F is replacing with the ID. Suppose you are giving the so ID for F. So then here is a T. So this T star F is replaced with T, and again T is replacing with the root node E. So but whereas in the top down approaches, so we start from the, so that is the root node and we can move up to the leaf nodes. So but here is when you are taking that, so here is we started with the leaf nodes, that is the identifiers, and next moving up to the root node. So this is the procedure for bottom up parser. So I have understood that. So that is here is in the parser. So that is the main objective that bottom up parse tree. We use the shift reduce parsing. Here is we use the shift reduce procedure for bottom up parsers. The general idea is to shift some symbols of input to the stack until reduction can be applied. So that is the shift reducing process means we can shift and we can reduce. So the first one is the shift operation means the general idea is to shift some symbols of input to the stack until a reduction can be applied. But whenever the reduction is applied, so then at each reduction step, if a specific substring is matched at each reduction step. If a specific substring is matched, then the body of the production is replaced by the non-terminal. Then the body of the the body of the production is replaced by the non-terminal at the head of the production. For example, you see that in the previous class, suppose in the example you have seen that. So suppose here is, suppose when you are taking that, here is F. So suppose F is replaced with the another non-terminal of that is the parent of that. So in the same way, here is, for example, so in this case, A tends to small a, small c or B. So in that case, suppose if you find this product is replaced with A. So instead of writing this product, we can write the A, that is the non-terminal symbol. So we can use the, that means at each reduction step, if a specific substring is matched, then the body of the production is replaced by the non-terminal at the head of the production. The key decisions. So in the bottom-up parser, the key decisions during the bottom-up parsers are about when the reduction, when to reduce and what production should be applied. So that is in the top-down approach, in the bottom-up approach. So there are two. So that is the complicated decisions you have to take. So one is the when to reduce the, so that is the parent with the productions and what production should be applied. Suppose for one non-terminal, if there are two or more productions are there, so which production we have to choose. That is the very, very important in the top-down, so that in the bottom-up parsers. So a reduction is a reverse of a step in a derivation. That means a reduction is a reverse of the step in the derivation. Generally, so we have derived the tree from top to bottom. So that is the left recursion. Also, suppose the top-down tree is already I explained that LL1 of parsers. That is the recursive descent parsers. So the recursive descent predictive parsers. But in all the cases, we derive the tree. Derivation means so we can start with root and we can end with the leaf. But in this case, in the reduction means we start with the leaf and we end with the root node. So that's why it is a reverse to the derivation. So the goal of the bottom-up parser is to construct a derivation in reverse. So for example, it is a root. So in the previous case, already I explained I star I. So that is the tends to. So this can be this ID is replaced with F. And next here is this F is replaced with T, and next this T is replaced by T star F, and next after that, so we are making the root node of this. So this is called shift and reducing parsers. That means shifting means so that is you can push the input character into the stack, state and input character into the stack, and the next reduce means the productions will be replaced with the non-terminal symbols. So these two operations are performed in the bottom-up approaches. So there are different types of bottom-up approaches are there. So for example, so first one is you see the LR parsers. See the LR parsers. So LR means L means left to right scan. So when you are considering the input string, so you scan the string character by character from left to right. And the next R means rightmost derivation in reverse. Rightmost derivation in reverse. That means in the rightmost derivation, so start in the reverse means from root leaves to root. And the K means the number of input symbols of look ahead. Number of input symbols of look ahead. So that means here is how many symbols you have to see at a time. Either no symbols you have to see at the time, or one symbol or any number of symbols. So in the string. So this is the LR parsers. That is LR parser. LR of K means that is the L means left to right scan, and the next one is the rightmost derivation in reverse R means so the number of input symbols of look ahead. So that is there are different types of LR parsers are there. The types of LR parsers. There are 4 types of LR parsers. One is the LR0 parser, LR0 parser, and simple LR parser. This is also called so SLR parser. SLR parser, SLR0 or SLR1 parser. Canonical LR parser, that is the CLR, and LALR. Look ahead LR parsers. So that means in the top down, so there are four approaches we can use in the construction of the compiler. So the first one is LR of 0 parser, simple LR parser, that is called SLR parser, canonical LR parser, that is the CLR parser, LALR parser. That means here that is a look ahead LR parsers. So in this class, I will explain briefly about that LR0 parsers and SLR parsers. So then with the gate problems and the solutions, right? So here is the comparison of LL and LR parsers. LL means that is the top-down parsers. LR means that is the bottom-up parsers. So here is, this is the thing, I don't want to go in depth about all these things. So the first is the LL of 0, and here is the some, this is included in the superset of LLR0 is LR0, SLR0 and LALR, and the final is LR1. So LR1 is nothing but so CLR parser. So that means here is the more powerful or more complicated parser is CLR parser or LLR1 parsers. So but more, so there is a very simple and general top to bottom of parser is so that is the LR0. So but here is also you can see that LL of 0 it is a top down, LL of 1 is also top down process. So in the previous session already I explained these two. So now you see that. So what are the advantages of LR parsers? What are the advantages of LR parsers? The first advantage is LR parsers are constructed to recognize all programming languages. LR parsers are constructed to recognize all programming languages. So that means, so it is better to go for bottom-up approaches. So because in the programming languages also we are using procedure-oriented and object-oriented. So procedure-oriented is the top-down, object-oriented is the bottom-up. That's why nowadays we are following the bottom-up. So that's why, so that is the bottom-up parsers are so very useful for generating any programming languages. The second one, the LR parsing is non-backtracking and shift-to-reduce parsers. So that means LR parser is a LR parsing is a non-backtracking and shift-to-reduce parsers, right? So already in the previous class, so we had seen that. So that is the backtracking is a very time-consuming process and very slow process. That's why we are eliminating that backtracking. But here is in all the bottom-up parsers, there is no backtracking. So that is an LR parser can detect syntactic errors. These LR parsers can detect syntactic errors so accurately. It scans input string from left to right and use leftmost derivation in reverse. So that is the principle. The principle of top-down parser is bottom-up parser is it scans input string from left to right and use leftmost derivation in reverse. Right? These are the advantages of using bottom-up parsers. So, for example, suppose the parsing algorithm. So, what is the structure of the parsing algorithm? So, that is how it will work. So, for working conditions, you see that. So, that is here is when you have seen that here is any LR parsers that contain input, output, stack, and parse tables. For example, here is the input we have taken A1, A2, A3, up to N, and the last character we make it as a dollar because here is we are using the stack. So that's why while we are matching the strings, so that is the first symbol should be, so we can use the dollar. So that's why here is, so here is we are using the stack. So the stack contains the, so that is a SM is a top state. We can call it the top of the stack. SM is the top of the stack. And here is XM. So that is all X's are non-terminal symbols. X's are all non-terminal symbols. And all S's are called the state symbols. All S's are the state symbols. Later we will go in depth about what is the state symbol, what are the non-terminal symbols like this. So here is, so we can use the LR parse engine. We can use the LR parse engine. But here is the entire all the LR parsers uses the parse table construction. Here is the, it uses a parse table construction. In the top-down procedure also we applied the, so that is a parsing table, but that parsing table was constructed by using a first and follows. But here is, so we can construct this parse table by using a different way. So that is, here is the scanner will scan character, the string, input string one by one, and here is the compiler construct. Suppose here is, so within that it will verify the grammars, that is the context free grammar and the parse generator. So that means here is, so but here is the symbol table can be constructed by using this, and based on that it will evaluate either the given string is so matching or not. So this is the entire structure of LR parsing algorithm. So but here is, when you are seeing that LR parser, SLR parser, LALR parser, CLR parser, so that is every procedure is same, but only the construction of parse table is different. Only the construction of parse table is different, and everything is same. That is, LR parsing engine is same for all bottom-up approaches. Right? So now we'll go that in depth about this values. For example, here is the LR parser consists of input, output, stack, driver program. This is nothing but LR parser engine, and parsing table. So here is next, when you see that the driver program is same for all LR parsers. The driver program is same for all LR parsers. So only the parse table changes from one parser to other parsers. Only the parsing table can changes from one parser to other parser. Suppose if you are using LR parser is one table, that is the procedure, just only that procedure also. So that is the minor changes, only minimum changes from, so that is the one bottom up approach to another bottom up approach. So suppose if you are good at only one LR parser, so the remaining are very easy to learn. In CLR method, the stack holds the states from the LR0 autonomous and canonical LR and LALR methods are same, right? So first you see that the driver program uses the stack to store a string. So here is, what is the use of that stack? So that means stack can be used to calculate. So the that it can be used for evaluation of the expressions. So here is, for example, you see that. So already I shown that. That is, here is a stack. Suppose stack will start with the S0, S1, S2, S1. That is the state and non-terminal symbols are state. So that is S of M always on the top of the stack. So that is the top of stack. Here is where SM is the top of the stack. So that is the SKs are state symbols. Later I will explain that state symbols. So because the state symbols are derived from the parse table. The X's are grammar symbols. Grammar symbols means that is the non-terminal symbols, or so that is the terminal symbols. But together the state and the grammar symbols. Together the state and the grammar symbol. That means a set of SS and a set of XNs. So together state and grammar symbol determine a shift reduce parsing decisions. So determine the shift reducing processing. So this is the stack. Okay. So that is the driver program uses the stack to store the string. So in this form, S of M is so that is the top of the stack, and here is XSR. So that is the grammar symbols and the terminals or non-terminal symbols. So whereas these are the states. So together the states and the grammar symbols determine a shift to reduce parsing. That means the main concept of bottom-up approaches are shift reducing, right? So now I will explain how to. The parsing program reads character from an input buffer one at a time. So that is how that will be checking. The current input symbols are used in the index. Index the parsing table and determine shift to reduce parsing decisions. So that means here is the program character by character. The current input symbol are used to index the parsing table. Suppose if you want to construct the parsing table, we require that letters are, that is the string characters are represented as indexes, and determine the shift to reduce parsing method. In an implementation, the grammar symbols need not appear on the stack. So while you are implementing that, the grammar symbol may be eliminated from the stack. We can have only terminal symbols in that. So suppose you see the parts table. What do you mean by parts table? What is the function of that? What is the function of this, right? So already we have studied that is a stack. So then generally the stack can store the values. It can be used to evaluate the expressions, right? So next parts table. So what is the use of that parts table? How to construct the parts table? The LR shift reduce parsers can be efficiently implemented by computing a table to guide the parsing. So throughout the parsing, so that means it can evaluate so with the directions or instructions of, so that is the parse table. So the parse table consists of two parts. One is the parsing action functions and another table is go to functions. You see that? So that means here is so action table and go to table. That is the two parts, right? So then here is what is the use of action table and what is the use of parsing table. So here is consist of action function and go to table. So that here is the action table. What is the use of that action table and how to construct? The action table specifies the actions of the parser. So for the shift to reduce or for a given parse state and the next token. That means the action table specifies the actions of the parser for the given parse state and the next token. So this contains rows or state names. That is the rows are called as state names and the columns are terminals. The columns are represented terminals. Let us show that, right? So here is you see that LR driver program. So suppose here is, so in that case, suppose when you are using the parsing table, action table. So what are the operations we can perform on the action? So generally here is LR driver program determines SM. What is the SM? It is the top of the stack, the state on the top of the stack, and the AI, the current input symbol from the buffer. So it takes the top of the stack and the input symbol from the, so the current buffer, that is the input string, and then consult action of SM and AM, which can take the one of the four values. So that means what actions it perform? Either the given expression is shifted. Shifted means that will be pushed onto the stack or reduced. That means the productions are replaced with the non-terminal, or either you have to say that string is accepted or not. That is the accepted or not. If there are any string, that will be displaying the error message. So I want to show that. So that is the parse action table contains four actions. One is the shift action, another one is the reduce action, accept action, and the error. So already we studied that accept means that the string is accepted. If the input string is matching, it will get accepted. If there are any errors, errors will be displayed. So the function of that action table is this. For example, you see that if action SM comma AI, here is SM is the top of the stack and A is a input character, input string character is equal to shift S. So if it is equal to shift function, so we can take the shift in the action table, right? So if it is equal to shift S, then where S is a state, suppose if we have taken the states are constructed in the action table or as well as in the body, where S is a state, then the parser pushes A and S onto the stack. So suppose shifting means, I think you understood. So suppose when shifting action, so that is if action is shifting, so then the symbol table as well as, so that is the symbol, the way, so that is the terminal symbol will be so pushed onto the stack. That means where S is a state, then the parser pushes the input value and the state name onto the stack. Suppose if action is equal to reduce, if action of SM comma AI is equal to reduce, that is A tends to beta. Suppose A tends to beta. So in that case, so SM is a top of the stack, A is a so input string character from the input string. Here is the reducing. Reducing means simply the productions are replacing with the, so it's non-terminal. The productions are replacing with the non-terminal. Then here is in the reduction phase, then AI and SM are replaced by A. AM and SM are replaced by A. That means here is, so that is the production AA, AM and SI will be replaced with the non-terminal symbol. Non-terminal symbol. That is called reduction. If S was the state appearing below A in the stack, then go to S comma A is consulted and the state pushes onto the stack. Here is, so suppose here is the stack already, that is the stack was there. So in that cases, so then here is we can call the go to table and then we can push the another stack. So next that is, if action S of M comma A of I is equal to accept, then parser is completed. That means string is accepted. So if action S comma M is error, then parser discovers error and then error message will be sent to the, so that is the error handling tables. So these, so that is action table performs these 4 actions. I understood that. So the action table performs these 4 actions. So because in the gate, so there are only 2 types of questions are there, 1 marks questions and 2 marks question. So in that cases, they may be asked this kind of questions like this. So that is if action is equal to, so that is based on the actions and go to tables. So next one is the go to table. So second one is a go to table. Go to table specifies which states to put on top of the stack after a reduction. The go to table specifies, later on I will show that how to construct the go to table and action table. The go to table specifies which state to put on top of the stack after the reduction. That means the go to state table, it contains only non-terminal symbols and it will specify that which non-terminal symbol you have to replace with its productions. So it contains the rows or state names, same as rows or state names. Columns are non-terminals. But where the in the action table, the columns are terminal symbols, and here is the states, the rows are common, and the non-terminal, the go-to table, columns are non-terminals. Non-terminals means capital E, capital A, capital S like this. Terminals means all the small characters. The go-to table is important to find out the next state after every reduction. So that means here is a reduction means the production is replaced with its non-terminal. So but here is when you are using that, what non-terminal. So suppose after reducing, so that is the which non-terminal we have to consider. That will be so guided by the, so that is the go-to table, right? Go-to table is indexed by state of the parser and non-terminal symbol. So suppose this is the go-to statement. So now you see that. So but in this case, I think you understood that. So that is the action table. So next to go-to table, and the next one is the stack in the structure of LR parsing. So next here is right sentential form. So these are very, very important. So again, suppose for the small questions, right sentential, left sentential, like that. So another one is we can use. So that is the first I will explain the terminology. After that I will solve the problem. Right sentential form is a sentential form in a rightmost derivation. Right sentential form is a sentential form of rightmost derivation. Suppose when you are taking that in the rightmost derivation, we can consider the values like this. Only these are the sentences. Viable prefix is a sequence of symbols. Viable prefix also very, very important. Viable prefix is a sequence of symbols on the parsing stack. So suppose when you are taking this, but for example, you see that how to push so these characters into the stack. That means in the reverse order we can push. So viable means that is the feasible. Either viable prefix is a sequence of symbols on the parsing stack. Suppose you take this is the within the bracket S of S. So this can be evaluated from this 1, 1, 2, 3. So suppose bracket from left to right we can parse like this. So now you see that, so LR parsers, right? So now we will construct the LR parsers, what it requires. So but I think I have understood that LR parser engines, so that is the bottom up parsers engines, so that contain what input contains, what the stack and what the parse table contains, that is the action table and go to table, and it reads the missions, right? But internally, what is the engine that will do? LR0 parsers. So here is LR0 parser is a shift reduce parser that makes use of deterministic finite automata. It makes use of a deterministic finite automata, recognizing a set of all viable prefixes by reading the stack from the bottom to top, by reading the all the symbols from the stack from bottom to top. So that means here is a viable, all viable means all, so that is a reliable, also suppose all correct, a prefix is. So the last one will show that what is the prefix of this. So if a finite state machine that recognizes viable prefixes of the right sentential form is constructed, so that is if a finite state machine that recognizes a viable prefixes of the right sentential form is constructed, it can be used to guide the handles one. So that is the handle selection. Handle is a substring that matches the body of the production. That is, the handle is a substring that matches the body of the production. For example, handle is a right sentential form plus position where the reduction can be performed and production used for reduction. For example, in this case, you see that in the first case we are using the dot, the full stop. So, but when you see that, so the entire expression production had been seen. So that's why here is, so that is here is the width, that is the handle is we can call as epsilon. So here is, so that is the dot is in between these two. That means I had seen the productions of, so yes within the bracket, but I did not see this. That's why here is with S handling is S. So that is the S, that is the stack pointer like that. So suppose here is the, so the pointer that is that specified within the string, that is the handle. For example, you see that handle pruning means, so reducing process. Handle pruning specifies that the reduction represents one step along the reverse of the rightmost derivation. So that is the pruning means you have to it perform the reducing process. For example, write sentential form in the given expression id star id. Already I explained that input string. And from this, first what character we have to take. Suppose here is when you are taking this id, so then we take the handle is id. That means this is assigned to id. So reduction process is, so id is replaced with f. id is replaced with f. So next f and this. The next one is again we are taking the handle. Handle is f. Handle is f. That means what is the next character we are taking from the string, that is called handle, right? So the similar way we can take the handle reduction. That is generally handle pruning means, handle pruning specifies that the reduction represents one step along the reverse of the rightmost derivation. So next one is augmented. But suppose when you have to use the bottom up parsers, so compulsory you have to convert the context free grammar to augmented grammar. So augmented grammar means, suppose here is the first one is that if G is a grammar with the start symbol S. So already I explained that every context free grammar contains the start symbol, that is in the bottom or top down approaches or anywhere it is a root node, right? If G is a grammar with the start symbol S, the augmented grammar G slash is G slash is G with the new start symbol, S slash, and the new production is S dollar. That means, so whatever the simple thing is, augmented grammar means whatever are in the context free grammar. For example, the purpose of the, so that is here is when you are using that augmented grammar. So that is the context free, we'll add that is the root, above the root we can add one more production. That production is S slash is equal to, so S slash is extended to, so S dollar. This will be adding, and next we can, each and every production will be represented with the dot notation. The purpose of the augmented grammar is to indicate that the parser, when it should stop parsing and announces acceptance of the input. The main aim of that augmented grammar is it verifies either when you have to stop the parsing the productions. When you have to stop the parsing productions. That is the very, very important with the augmented grammar. But how to get this augmented grammar? So that means here is that is the augmented grammar means, for example, you see that here is we can say that this is the, so that is LR the context free grammar, and here is we can say that E is equal, E tends to T tends to E plus T, and T tends to this one. Suppose here is when you see that this is actually context free grammar. This context free grammar can be so added one more top expression, that is called, so that is called here is S can have the, so that is S can have the form of E, that is the E, and the same E we can use rule 1, that is the S can tends to S slash. So that means in the argument you see that the context grammar and augmented grammar means, so here is the first one is, so that is the root can be changed with another, so dummy, another dummy state root, and next here is all the productions which start with the dot. All the productions start with the dot. So then we can call it as a augmented grammar. Then we can call it as a augmented grammar. I've understood that we can take the context free grammar and we can put the, so that is that we can replace the root node with the other productions. So after that, each and every production at the right hand side so can be prefixed by a dot notation, dot. So then we can call it as a grammar. It is a called as a augmented grammar. So it will verify that if the dot is comes this side, so we can say that it is a visited or not visited like this. Later on with example I will explain that, right? So that is the augmented grammar. So next one is we can use the LR0 items. So we have to, here is also we have to create the LR0 items. LR0 items of a grammar G is production of G with a dot at some position at the right side. Already I shown that in the augmented grammar, so we can use the dot notation. For example, in the production, A can have the form of XYZ is the 4 items. For example, here is we can say that it is a first item because this is not item. So this is the production. A can have the form of XYZ. It is a production. So we can call it is a form, but whenever the production having dot, we can call it as a, so that is the LR item. So that means here is when you see the dot is in this case, we hope, what is the meaning of this? We hope to see a string derivable from XYZ not next on the input. That means here is, well, we have not seen up to this time XYZ productions and the values. Or suppose when you are saying that A can have A tends to X dot YZ, that means, so I have seen all the productions of X, but I did not see the Y and Z productions. So next that is the thing. Suppose here is A is equal to XYZ means here is I have seen X productions of X and Y, not see the productions of Z. And here is I had productions of X, Y, Z. So this is the final state. We can call it as a final state. In the augmented grammar, so that is this kind of things are called LR items, right? These LR items are important. So next one is, so that is the production A can have epsilon generated only one time. That is epsilon is there, only directly we can put the dot and each of this item is viable prefix, but when you are using that it is a compulsory. So second one is the closure item. Next one is closure item. So that is the closure item. An item created by the closure operation on the state. An item created by a closure operation on a state. So that is the closure operation means that will be having 0 or more productions or 0 or more states. So complete item. So that means here is you can use a complete item. An item where the item dot is at the end of the RSS. Already I shown that. So if the complete item means, suppose if an item, whether the item dot is shown at the end of the production, we can say that it is a complete item. Otherwise, it is called as so not complete item. Then we have to complete it. So these are the things. For example, you see that with example, I am explaining LR0 parser. So clearly you observe that. So what I am doing, right? In the LR parsers, just first thing is, the first step is, so when you are considering context free grammar, we have to convert that into augmented grammar. So how do you convert that LR0 parsers, context free grammar to augmented grammar? So first one is the root node is, so that is we can create the dummy productions, so before the root node like this. Suppose actually this is the, so context free grammar. So for this grammar we are adding a separate node, that is S can have the form of E, or sometimes you can suppose if it is S, or here is E is equal to E slash, and here is you can use the E slash like that. That is the rule one. So after adding, so that is the dummy root to the context free, the dummy starting symbol for the context free, then use the augmented grammar. That is, all the productions should start with the dot. You put the dot for all the productions. So suppose S can have the form of this, you can use the dot, E can have the form of dot, and E can have the form of dot E plus dot. So next T dot and E dot. So that means here is we can put the dot for all the productions, right? Now we can say that it is a augmented grammar. In the LR0 parser we can construct, that means we can dummy root node will be created, and next all the productions prefixed by the dot notation, that grammar is called augmented grammar, right? So now construction of LR closures. LR closures means, suppose here is that items you have to create up to this. For example, just you clearly observe that. So suppose here is in the closure items, based on the closure items only we can identify the states. So based on the states only we can construct the, so action table as well as go to table. Now how to construct the LR0 parser closures. For example, so first you see that first augmented grammar, this is first we are considering, in the first state we are keeping all the augmented grammar same. So that is, here is S naught. This is the state. We are assuming that it is a S naught is a state. We can assume that S naught is a state, starting state. S tends to dot ES and dollar is there done. So that is the for starting symbol. We can put the dollar symbol. E tends to dot T. E tends to dot E plus T. T tends to dot I. T tends to dot of this. So after that, so now we can parse it. Suppose first we can take this and E, first symbol on input E in this thing. So we can construct, that is E. So on input address and input E, that will enter into the state 1, that will create state 1. How that will be entered? So that is after seeing the productions of all E's, that will enter. So here is how many E's are there? S can have the form of E. So in this case, only dot will moving one position. Dot will be moving to other position. E can have the form of E. Again, this is E. All the E productions we are writing here. Dot E plus T. So then we can call it as a state 2. So after that, again we can take this. S is equal to S dollar. Then you can then dollar. On input to dollar, so it will enter into the final state. It will enter into the final. That is the complete item. Clearly observe that. It is a complete item S2, S1 and S2. Complete item we are creating. So after that, you take the second projection on input. So suppose dot is there. That means already we have seen all the projections of E. Then here is the dot is there. Next, on input plus, that will move to an input plus, that will move to other state. So here is an input plus, that means, so then here is the dot comes to this place, that is the plus has come left side and the next dot comes to this side. But here is, so if the dot is prefixed by any non-terminal symbols, all the productions of that non-terminal symbol should be written in this case. All the non-terminal, suppose the dot T is there. Dot T means, what are the productions of dot T? That is the T dot T tends to dot I, we are written. So T tends to dot, so that is the bracket E of I, we are written. That means You understand that? Suppose if it is a dot is before the non-terminal, we have to write all the productions in between of that non-terminal. So then here you see that on T, that will write the, so that is the T, so that is here is that will ended. So that means it is also comes as a final state. That means in this case E, so that is it is completed, E plus on T, so then this is completed. That means E, so here is you get the product of E is to E plus T dot. So that is the complete item we got. When you are getting the complete item, we can represent the complete items with the double circle. So suppose on I, in the second projection you take that is T dot I, so then I is goes to this place. I on I, it will enter into the fifth state. So that is when it enter into the fifth state, so that is the dot will be moving from right to left to right, one by one, when it enter into the state. So here is also I dot, dot is at end. After dot there are no things, we can call it as a complete item, we can make it as a doubles. So this is the standard. And on this I, suppose the same I, here is also I dot. So the same will be reached to the same I. Suppose if two or more are getting, we can connect it to the same final state. So here is on T, second one is E, on input T. So that means on input T that will enter into the this one. T dot is, this is called state 6. We can create, this is the state 6. And next here is on the bracket. Suppose here is the bracket is there. So in this production, before the dot, after dot we are having the bracket. On a bracket that will enter into the 7th state. But here is whenever you see that again, so that is before the non-terminal, so that all the E productions you have to write in this case. For example, this is same as like this. This is called 7th state. Again you start with the dot. Suppose here is when you are using that. So on T, suppose here is in the on T, here is on T, second projection, dot we are taken. So that is on T, it will enter into the state 6. Again that means the second projection. And next here is suppose in the braces. So that is an input to input open bracket. So that enter into this. But here is an the same input that will be in the same state. Suppose in this case, so T tends to dot E within the bracket, that will be in the same state. Understood that? So next one is E, on E, that is in this production, T tends to dot this one, and the next E, again we can consider this entire table will be considered like this. So now, so this is the final closure of items, final closure of items. So here is we have constructed this closure, and based on this closure, so already I explained that in the stack we can push the input character as well as state, input character and as well as state. But here is we see that how many states are there? State 0, so that is the next one state, 2 state, and the third state 4, and 5, and next 6. Also suppose 7, 8 and 9 states are there, 9 states. We can call it as a, so that is the thing. But there is, here is the graph I am taking. There is another method is there for finding the states and closure of R. And so that how we are getting the states, it is a very easy. But if you understand, so suppose it is animation, you go through that, and suppose here is the only thing is, so that is that every symbol moving from one state to other state, the dot will be, so that is moving to right side by one position. So that is if the in the new position, so suppose if the dot is, so before the all the productions of non-terminals will be so written in that state. Again we can do the same process of this. So there is so that is another way of constructing. Suppose if sometimes if you think it is difficult, then you take that another one for construction of LR items. I naught, suppose the same methods are written in the first state. So go to, so that is I naught E, that is the, here is I naught is the state 0. So there I have taken S1 and S2, but here is I naught, I1, I2 are the states. So that is an input, the first state. So on S is equal to, S tends to dot E dollar. So that means here is on first move that go to the state 1, and here is that is the state 1. So next state 2, whatever you got there, here is representing with this So symbols like this. So next S dot. Suppose S is dot. So then here is written the productions of these two. And the next here is dot S dollar. So suppose in the I2, so we are getting the state 2. So suppose on input dollar, it will enter into the state 1 to state 2. Assume that. So that is on input plus, it enters from so state 1 to state 3. So that is like this. So that means, so then all the productions we can write. So whatever are written there, that will be written like this. So after this, so then you can construct the DFA. You construct the DFA of this one. So DFA means simple. So that is the simple form of that one. We can construct the DFA. You see that EI, because here is suppose when you see that just here is T E R F or something we are written like this. So that's why S not S1 S1 instead of S1 S0. Here is taken that I1 I not like this. Suppose on E it will enter into the state 1 and on dollar it will enter into the state 2 and I, so suppose on I it will enter from 0 to state 5 and the next T, so that will enter into the state 6. Already I have seen that that is the only simplified, that is in the simplification of this one. So that is the form we are written. So this is the DFA. So it may be somewhat difficult, but for the things this will be same, right? But here is based on this one, you can construct the LR parsing table. You can construct the LR parsing table. So just you see that how we are constructing, but LR parsing, so that the parse table that contain the states, number of states. But how many states are there? 9 states are there. So, but you can see that anywhere that we can find the 9 states, right? So that is the state 9 or 9 states we are having, that include 0 to 8 means 9 states. And here is also you can see that 9 states, yes 9, right? So that's why here is 9 states are there, just why we have written this. So that is the 0, 1 to up to 8 states and last one is the, just we are given that 9 states, 0 to 9 states. Suppose 0 to 9 states means 10 states are there. So but here is this input, it is called, so that is the action part. Up to this one is the action part and this part, this table is the go to parse table, go to parse table. So here you see that, so but when you are using this, suppose when you see that it is a action part and it is a go to part of the table. But how we are constructing the action part? So in the action part, the number of columns specifies all the terminal symbols, all the terminal symbol. I plus left brackets, right parenthesis and dollar symbol, and the go to state that contains only, so that is the capital letters, that is the non-terminal symbols, right? And so that the number of rows are same states, and next in the action table we can having only, so that is the small letters. In the go to part table we are taking, so that is the non-terminal symbols. But how we are constructing, you see that how we got this 5 0 state. So that is on input I, so that is the that will moving from 0 state to which state? You see that. So on input I, so on input I, it moves from 0 state to I5 state, I5 state. So then this 5 is writing here itself. That 5 is writing here itself. So that means you say that, so suppose in all the states, suppose 0 to, suppose 0, from 0 to on input left braces, it will goes to which state? You see that. So from 0 to left braces, that will go to the 7, I7, I0 to I7. But you see that with the here is we are writing state number, that is the 7. And the next one is, see the on 0, so that means a non-terminal symbol. Suppose if we have taken that, so then here is on 1, 0, so that is on E, so suppose which state it will go to. Suppose here is on 0 to on E as input, it will go to the state 1. So that's why here is we are written state 1. Our next T, suppose you see that, so that is on 0, it will enter on 0, for input T, it will enter to the I6. Then we are written this 6. Our next, suppose we say that one state, from state 1 to on I, but there is no I, suppose for one state, On input I, there is a no outgoing. On input state 2, so suppose state 1, on input plus, it will enter the I3. I1 to I3. So then here is, we can write the state number 3, and I2 on dollar, it will enter into the second state. Suppose on 1, so suppose on input 1, I1 to I2, it will enter from I1 state to I2 state on the given input dollar. So in this way, so we can construct all the things. But here is yes, so dollar, yes tends to S dollar. So then here is, we can call it as a accepting state. That is the final state, right? So if we want to find out that the string is true or false, string is correct or not, then we can use acceptance. Here is, sometimes we can write the acceptance state, but all the unfilled cells are called as a error. Already the action table contains F4 actions. So that is the shift, reduce, error, and so that is the error. So that means here is the 4 actions that will be taking accepted. So this is the accepted string, or whenever we are taking that, these are the unaccepted. But these are, we can use the reductions, we can call it as a reducing. Here is reducing, but here is, when you find these things, we can use the reducers. But here is why you have taken the LR parser in the reducers. So but it, irrespective of any symbol, it will be replacing the productions. That's why we are calling it as a LR0, so LR0 parser. There is no lookahead for this one. But now I have understood that how we have to construct the parse table. This parse table is same for almost all the 4 types of. So that is, the construction is same as 4 types of LR parsers, but there are a small minor differences. So if you understand only one how to construct the, so that is the parsing table for one, the remaining thing you need not to bother about that. Just only minor changes. I don't want to explain all those things. Just only I will explain when that go to that. Only I can solve the problems, but I never explain again the entire thing, right? So this is the construction of this. After constructing this table, so how to find either given string is accepted or not based on this one. For example, you see that. So the stack, input, and action. But here is, you see that. So that the stack. So we are pushing S naught, the starting state, under the stack. That is everywhere by default we can push on that. And here is, I am taking input string. I place within the bracket I plus I. Either you have to verify that either the string is accepted or not. With the help of this acceptance table, we have to construct. So suppose here is I plus I a dollar at the input symbol. At the end of the input expression, we can put the dollar sign. So the first thing is, you see that. So here is, so but here is, you see that I. So suppose stack, you see that stack is state 0, and here is the input symbol is I. So that means here is on state 0. So it moves. You see that it moves to, that is from on input I. It moves from state 0 to state 5. So then here is, that will be having the number. So then we can push this, that is the shift these symbols into the stack. What you have to push? So that is the I, this I value, and the next state. What is the state? I state. That is I5. So I5 is there. I5 state is pushing onto the stack. And so this is the shift operator, right? So in the shifting operator, exactly what we are doing. So first we are taking this within the stack. 0 state is there. From 0 state to on input I, it moves to which state? It moves to which state? On 0 from 0 state to on input I, it moves to state 5. State 5. So then here is, so we can push that state as well as that I. So that is I and S5. So after that, but when you see that S5, so that is the S5, and the next that is the plus. Suppose when you see that S5 and this I, so then when you see that S5 and 5, so then you see that here is the reduction is there. So that is the S5, state S5 and I. It will verifying these two. So that is I as input state 5, but it is, this process is reduction. That means here is I5 and I7 is reduced by this. That means I is replaced with the T from the expression. Then that is the upper state, that is the parent state. So then with the parent production we can. So next one is, you see that T and S6. So that is the T and state S6 is this, and the state and input T. So then here is you go to the input T6 and the input T. So this is a blank. There is no thing. That means it is a time for reducing. Here is written. So where you have to reduce and where you have to shift the process. So S and S6. So then T is replaced with E. That is the, we are moving to top to right. So that is I is a lower level, next to T, next to E. So after that T is replacing with E, and next you see that on input E it moves to state A or not. Suppose input E state 1, you see that an input E there is a gap, no gap, and here is you see that, and so that's why here is, so you can shift the procedure. So you shift the values, that is S1 E is equal to, so S plus and next to plus F, that is this place is pushed onto the stack. Along with the stack, that is the same number, we can use S3. So that is the S3, right? So then S3 will be pushing onto this. Our next one is in the same way S3. Again you take that state 3 and plus. Next, suppose when you are taking state 3 and plus, so then there is a value that is also, there is no values that will be. So next again shift is there. So then shift this value into, push onto the stack, either state and symbol, right? S7 and parenthesis of this. Our next one is plus I dollar, it will reducing the reducing state. So next here is, so suppose S7T of this. So suppose here is T and S6. You see that state 6 and T. There is no, that is a reduction. That is reduced T. But here is the only thing is, you have to decide, so which production is replaced with which non-terminal symbol. That is a very, very important, right? So that is the S6, T S6 of this one, so reducing this. That means T is replaced with E. You can replace with the E. So after that you see that S0, S1, S7 and 8 and E. So suppose this is the input. So on input S8. So suppose is there anything? So state is 8 and next on E. So there is a no wait. So then again, so suppose on state 8, so that is 8, there is a value. So that is the state 8. So then that will be, this is also pushing onto the back of this. The plus and S3 is pushing on plus and S3. That is here is the S3 and the stack of the 7 position will be pushing and reduced by this. This process will be done. So the finally, so you can do like this, right? So finally you can get the value of this, and finally whenever you find the dollar symbol, here is dollar. So then here is S, the dollar symbol. When you find the dollar symbol is pushed onto the stack, so that here is thing is accepted. So this is the procedure. So that is once again you practice. Once again, suppose the first time you may not understand this one, but here is created animation with animation, how to create the states, how to create the augmented grammar. So what are the LR parser items, item closures, and next that how to get the string by using the thing. So that is you go through this example. So then easily you can understand LR parsing of this. But here is you see that only, but here is suppose whenever you are finding the reduction state, so all are making it as a 1. So suppose I plus than, so just only I had given the one line, and here is also single line. See, that means here is LR0 means it is not looking on any input character. It is not looking on any input character. So that's why we are making it as a LR0 parser. We are making it as a LR0 parser. For example, so suppose in the CLR parser, only difference is, suppose in this case, there is the chances of getting shift reduce conflicts, because here is, so that may be, entire thing is reducing means there may be chances to get the concept of that one. So this is the LR parsers. And what are the main drawbacks of that LR parser? LR0 is a simple technique in in the family of LR parcels. LR0 parcels are too weak to be of practical use. Practically, it is somewhat difficult to use. LR0 accept only small class of LR0 grammars because if conflicts occurs. Because why conflicts occurs? So it doesn't see any input symbol, but simply it will be reducing based on the states. That's why there may be chance of instead of reducing the I productions. So if you are reducing that is plus left branches or plus productions, then there may be conflicts may be occur. So next one is there is a fundamental limitations of LR is the no look ahead token are used. LR0 parsing is the weakest and it is not used much in practical. So these are the main things of LR0 parsers, right? I think you must have some patience to listen. So there is the top down parsers, but it is a very interesting, right? Suppose if you really so concentrate on that, so then you can take it as a challenge to implement it, right? So, but what kind of questions we are getting on in the gate on LR0 parsers? So, some questions I will explain. After that, I will explain LR parser. Gate questions. The first question you see that already in the previous class. So that is the same example I explained, but there I have taken so that is the question is different, but here is the question is different. So first question you see that consider the grammar E tends to E plus N or E into N or N. This is the context free grammar. For a sentence N plus N into N, the handle in the right sentential form of the reductions are. So suppose here is the handle is in the right sentential form. Right sentential form means it uses rightmost derivation in the reverse order. Right sentential form means that's why you remember the terminology. The right sentential form means it. So that is it uses a rightmost derivation in the reverse order for the reduction of the tree. So in the GATE 2005, so you got this question. The answer, suppose you see that A is equal to N comma E plus N and E plus N into N. So B, N comma N plus N and N E plus E into N. So that is N comma N plus N and N plus N into N and E of N plus N like this. But here is when you see this question, which one is the correct answer of this one? Here is we are using the right sentential form means from right to left we have to evaluate the procedure, right? So the bottom to top. For example, you see that explanation. You see that E can have the form of E star N. That means first we are considering this production. Either you can consider this production or this one or the, but because here is, so from right evaluate, suppose here is you take N into N. So that is here is, so that is the E star N. We can take the E tends to E star N. So suppose here is this expression E star N, we are taking this expression. Applying E star N, that means the second production we have taken first. So after that here is you see that. So that is the E can have the form of E plus N star this one. So here is, so second that is the E is, that is here is, the E is replacing with the E plus N. You see that, so the second production, first production we have taken. So that is here because you have to get the, so that is the N plus N star. That's why here is the first we have taken star. So that is the leftmost, so that is the rightmost sentential, E star N. So that is the E plus N star. That means E is replaced with the E plus N. So that is here is also very important to select which production you have to replace, right? You have to choose the replace. So next here is this E can be written last N. It can be written with the N production. So that's why here is E is equal to N plus N star N, applying E rule, that is E production N. Hence the handle is the right sentential form in N. So it is a right sentential form in the N. So hence option is the right choice. That means here is the D is the answer. D is the right answer. But here is when you are taking that, but here is the two sentences. First we are considering this and second we are taking this production, right? So based on these two productions and with n, so we are evaluating the process. But here is what we are given: n, e plus n, and e plus n plus. So then we cannot get the answer for this one. So next here is e plus n. So we cannot get the answer for this, because here is we can get the 4. Suppose here is we are getting n into n plus and n reproductions. Here is the optimal. There may be chances to get any number of trace, but here is you have to take the optimal. That's why this is the question number for question number. So that is the D is correct answer, right? I understood that. So the minimum number of productions we have to use, and we have to use the right sentential form, and so we can implement the either given string is derived or not. I understood that this question. So here is you are taking the productions. So that is when you are taking, suppose you consider these productions. But here is the e is there and e plus. When you are using that, again you can get n plus n into or something. But here only we can get. That's why D is the correct answer for question number 1. So next one, you see that question number 2. A bottom-up parser generates what? The leftmost derivation in reverse, rightmost derivation in reverse, leftmost derivation or rightmost derivation. Which one is the correct answer? So that is the B is correct. B is correct, because here is the bottom-up parsers uses rightmost derivation in reverse. Rightmost derivation in reverse. That means right derivation means it starts from root and it ends with the leaf. The reverse means here is start with the leaf and ends with the root. But in top-down parsers, it starts with the leaf and it ends with the root. So that's why it uses, the bottom-up parsers uses rightmost derivation in reverse. You got this for 1 mark question, right? Rightmost derivation in reverse. Suppose if you are good at the definitions or that is the terminology, so then it is easy to answer for this kind of questions, right? So next one is that is the bottom-up parser generate rightmost derivation in reverse. That is the option B is correct. So next question number 3. You see that question number 3. Consider the following statements related to compiler construction. So many times I have seen this kind of questions in the GATE, right? Consider the following statements related to the compiler construction. So that is the 2 statements here given. Lexical analysis is specified by context-free grammar and implemented by push-down automata. A lexical analysis is implemented by context-free grammars and implemented by push-down automata. Second one is syntax analysis is specified by regular expressions and implemented by finite state machines. Which of the above statements are correct? That means they are given 2 statements. You see that either only first one is correct or second one is correct, or both 1 and 2 are correct, only correct, or otherwise neither one or nor is the correct answer. Which one is the correct answer? So lexical analysis is specified by which grammar it can use. Lexical analyzer uses regular expressions, but not context-free grammars, and it are implemented by finite automata. It is implemented by finite automata. Already I explained that NFA and DFA. So that is for implementation, and for specification of tokens. Already we have studied the regular grammars. In the syntax analysis, it's specified by what? Context-free grammars, and implemented by finite state machines, and implemented by what? Push-down automata, or parse trees, right? Or stacks. So that's why here is the both the sentences are wrong. Both the sentences are wrong. That's why answer is D. Neither one nor two are the correct. Understood that? So theoretically, if you are good at basic concepts, then only you can answer this kind of questions. But most of the students, 90% of the students, exactly what they are doing. So they are not concentrating on theory and they are concentrating only on the problems. Without knowing the basics, without knowing the fundamentals, it is highly impossible to answer the questions. That's why. So even some lakhs of students they are writing gate examination, but very few students they are getting. But because so that is the lack of fundamentals, right? So, but they are good at subject, but actually fundamentals are very important. Analysis and problem solving skills. So that is so both the statements are wrong of for detailed information on lexical analysis and syntax analysis. D is correct answer. So question number 4. Which of these is true about LR parsing? Which of these is true about LR parsing? So I have given 4 options, but I have collected these questions and answers from the net, right? So that's why. So that is the most general non-backtracking shift reducing parser. Is the most general non-backtracking and shift reducing parser. B is it is still efficient. It is still efficient. C is both A and B, and D is none of the mentioned. D is none of the mentions. But these are all gate questions, but not any other things. But here is in this case. So I took the questions from the gate books and previous gate question papers, right? I collected from 1993 to and 2019, right? So here is the so that is the most general non-backing. So that is then is the most general non-backtracking shift reduce parsers. It is still efficient. So that means already in the introduction of LR parsing, I explained that it is the most general non-backtracking shift reducing parser. So A is correct, and it is still efficient. It is still efficient. That's why the extensions CLR, SLR parsers are using LR1 parser. That is the very efficient CLR1 parsers are efficient. So that's why answer is C, both A and B. Answer is C. That is the both A and C. But these two I explained in the beginning class of the LR parser, in the introduction of LR parsers, right? Both A and B are correct. So that is the type bottom up parser that efficiently handle determinate context free language get of this one. So next question number 5, you see that. Which of the following is incorrect for the actions of a LR parsing? So which of the following is incorrect for the actions of LR parsing? So one is shift S, reduce A tends to B, third one is accept, and fourth one is reject. And which one is true? That is, which one is following is the actions? Which of the following is incorrect? So that means here is, but when you are taking that, so which one is the correct, incorrect? Already 4 are there now. Shift, reduce, accept, error. Is there any reject? Error means that is rejection is the, if you find the error, it rejects. Reject is not a answer. So that's why the answer for this 5th question is C. So that means the first one is shift is correct, reduce A tends to, beta is correct, B is correct, accept function is correct, and there is no reject, that is the error is there. So that's why here is C is correct. 1, 3, so 1, 2 and 3 are correct and 4 is not correct. So then here is suppose when you design the parts tree action table, so that it contains the four actions. One is the shift, reduce, accept, and reject. So next that is six. So next here is the sixth question. If a state does not know whether it will make a shift operation or reduce for a terminal is called. So suppose if a state does not know whether it will make a shift operation or reduce operation for terminal is called. That means you are shifting. So suppose here is suppose one is the shifting operation and action, another one is the reduction option, right? So suppose sometimes if the parser confused that either it has to take the reduction operation or shifting operation. So then what kind of error it displays? A is with the shift and reduce conflicts, reduce and shift conflict and reduce conflict. Which one is the correct? So generally we can call that conflicts is called shift to reduce conflicts. We are called not reduce shift, but here is shift to reduce conflicts. That is the A is correct answer. A is, so the same name suggested that the conflict is between shift and reduce, hence it is called as a shift to reduce, and then there is no reduce and shift. So that is the conflict is shift and reduce conflict. That's why we can give the name like this. Seventh question, when there is a reduce conflict, when there is a reduce conflict, four options. If a state does not know whether it will make a shift operation using the production rule I or J for the terminal, if a state does not know whether it will make a shift or reduce operation using the production rule I or J, so if state does not know whether it will make a reduce operation using the production rule I or J for terminals, and the next one is D, the number none of the mentioned. So here is which one is the correct? So a state does not know whether it will make a shift operation using the production rule I or J. So shift operation doesn't comes into reduce. So that is A is the correct answer. If a state does not know whether it will make a shift or reduce. So but in the B case we can use the shift and reduce conflict. But here is if state does not know whether it will make a reduction operation using the production rule I or J. So that C is the correct answer. So then here is C is the correct answer. So these 7 questions are from LR0 parser. These 7 questions from LR0 parsers. I understood that. So that is the question number 1, question number 2, question number 3, question number 4, and question number 5. So then here is, so next you see that LLR parser, briefly I will explain, SLR1 parser, but here is SLR1 parser, simple LR1 parser. So that is what is the main drawback of that LLR0 parser? Here is the conflicts will occur. So suppose here is a shift reduce conflicts. For example, here is whenever reduction operation is there, it doesn't depend on any input character. So it doesn't see, it doesn't look at the any input characters. So that's why there is chances of getting conflicts. But when you are taking this SLR parser, so for each and every input symbol, it will having separating. That is the look ahead. So that is instead of getting that is the total line, here is we can make it as a separate line. So that is also look ahead. But how to get the look ahead means by using first and follow function, we can find the look ahead. So everything is same. So just one briefly I will explain that. That is the SLR parser. The construction you see that. So that is the letters SLR simple left and right. That is the left indicate the input is read from left to right. The right indicate the right derivation built. So SLR parsers are simple SLR parsers. So I don't want to go in depth about this. Here is also items, but here is how to get this means that is with the follow of this. So the same augmented grammar we can take. For example, With example, I will explain that. In end, not to explain the theory because so time is only half an hour. So I have to explain some more gate problems on the SLR parser. So construct the SLR parser for the following grammar. The same grammar here is I have taken. So this grammar again you have to convert that into augmented grammar. How to convert that into augmented grammar? So the first we can use the dummy node with the dollar e slash and have the form of e and dollar. The same thing. This is the dollar, or you can put the hash. No problem. Anyway. So after that, so that is so give the dots. So that means this is the augmented grammar on a dummy root node and with the dot productions it's called a so that is the augmented grammar. And here is this entire augmented grammar. By using this, so item closures we can create. Already we have explained that. Item closures. It is state 0. So that is the state 1. So that is, I don't want to go in depth because the similar procedure what we took in the LR0 parser, the same procedure is to apply, but it is animations, we see that. So all we are creating this symbols. So this is the, so that is the closer. So after that, so the second procedure we have taken, this one. Based on this one, we are creating the states, right? So that is the DFA we are constructing because for easily understanding purpose, we are applying the DFA. Already we know that DFA means on any input symbol, it goes to only one state, not more than one state. So this is the DFA. From this DFA, so that is we construct. First thing is we construct the follow of that expression. So this augmented grammar we can take and find the follow of that one. Because based on the symbols only we can select the states. Follow of E is as already I explained that how to construct the follows. For this expression, follow symbols are this follow of T and follow of T. For non-terminal symbols, we can take the follow symbols. But we can construct. These are the reductions. In these reductions we can put it is our duty. Suppose all are we are keeping that R1, R2, R3, and these R1, R2, R3, R4 are represented as reducing. So that is the, so the, for the same thing we can construct the table S5, S6, so the same thing. But here is you see that, but in the fourth state acceptance state, but here is we are replacing that reducing. But the we are look ahead and SLR1 means, so then you see that we are looking plus, we are giving importance to the plus and we are using R6. And here is star reducing R6 or R6 like this. But there only for entire thing without considering these attribute, so these terminal symbols directly we are written only reduce operation. But here is for each and every symbol we are looking at the case. So that is here is we are constructing LR parsers like this. After constructing, either you have to you find the either string is accepted or not. In the previous case, already I explained the stack, but the same here is I am explaining with the animation. You see that the stack, input and action. For example, you consider that stack state is 0, right? State 0 is pushing onto the stack. There S of 0 I push. No? So next first symbol we are taking ID. So that is in that case ID. So that is in the previous case we have taken the that is the first symbol. So ID and this one. So which symbol you have to push? S5. That means say state 5 and ID push onto the stack. Then you see that. So this is the push onto the stack like this. So then ID 5. 5 is the state number and ID is the input value. So that is the pushing onto the stack. So after that second case you see that this state is 5 and state is 5 and so then what kind of what it is? It is a reduction phase. R6 is there, reduction. That means R6 is which state? So here is we are considering it now R6. So suppose for the grammar, be patient because so here is where we are assigning the reduction R1, R2, R3, R4, R6. That means R6 production can be used for reducing the statement. So that means here is the reduction R6. That means here is that will be replacing. Suppose is that so F tends to ID. So this is A6. So that will be replacing. That means 5 is replaced with the ID. So we are considering we are popping ID value and the state value. Both can implement this. Push onto the tag. That is the acceptance. So again you take the 0 state. That is the push the 0 state, and next you take 0, and the next reduction there FID is there, right? So next here is F. So that is after the ID and 5 state we are getting the reduction. Reduction is 6. So then that place is ID is replacing with the F. So that is F is comes like this. So next you take F is a non-terminal symbol. Then you see that 0 state in the F non-terminal, that is equal to third one. So then the third means, so just you take the 3. So 3 means, so again the third state is pushed onto the stack. So then third state is pushed onto the stack. So after that then you see that a stack 3. In the third state and given symbol is star. In the third state and given symbol is star. So then again reduce production. So that is the fourth reduction. Fourth reduction is what? This one. T is equal to F. T is equal to F. In the beginning I have shown the how to construct the tree. The same for the same year is where it is T. So then here is again when you are using that. So that is F3 is replaced with the T. So T. So then here is we are pushing a T into this one. Right? T. And the next T is the second and 2. So on the second, so next one is on the second T2 and then T. So on terminal. Just you see that. That is the start. On the state 2 and S7. That is the reduction. So then after that the symbol will shift onto this. The same procedure when you apply. So internal of the stack is also done like this. You see that how much time taken to construct this, right? But without teacher, the slides will speak, right? The slides will speak. So that is the thing. Suppose I am explaining this now. So without my explanation, if you concentrate on this animated outputs, then you can find the things of this. So that here is, so all the symbols we can use a top-down procedure. So this is the stack operation. So that is here is. So for this stack, I get the values of this one. This is the shift reduce parser. Shift reduce conflicts arises from the fact that SLR parser construct dimension is not powerful enough to remember left contents of this one. So that is the drawbacks of that SLR parsers. Cannot parse some LR grammars. So it cannot parse some LR grammars. So the main problem of SLR1 parser is look ahead information. Is added to LR0 parser at the end of the construction of base of this follow. But here is we have to use the follow set for avoiding the conflicts. But here is it is somewhat making the slower and confusing. LR parser we use the follow and parsers of this one. These are the drawbacks of this CLR. So what are the questions you can get on CLR parsers? So that is then you see that the first question from the CLR. Consider the following two states. Consider the following two states. So first one is statements. First one is P statement. Every regular grammar is LL1 grammar. Every regular grammar is LL1 grammar. Statement Q is equal to every regular set as a LR1 grammar. Every regular set as a LR grammar. Which of the following is true? Which of the following is true? Both P and Q are true. P is true and Q is false. Or C, P is false and Q is true. Both P and Q are false. So which one is the correct? So P, every regular grammar is LL1 grammar. LL1 means scan from left to right and use leftmost derivation and look at is 1 like SLR parsers, right? every regular statement as a LR1 grammar. Which of the following is true? But when you see that every regular grammar is LL of 1. LL of 1 means, but here it is a top-down process. That is LL1 is a top-down process. And so suppose every regular set as a LR1 grammar. So it is a bottom-up process, right? But when you are using the every regular grammar is means, sometimes the regular grammar may be having some problems. What are the problems? One is the ambiguity, second one is the left recursion or left factoring. If any grammar having the left recursion, left factoring or ambiguity, any one of these top-down process fails. Because we are taking every regular grammar. Definitely some grammars will be taken. But here is every regular set as a LR. Every regular set means, so a constraint, so that is a well proven, that is a without, so that is a ambiguity or something grammars. That's why here is in the SLR1, so it will construct from bottom to top, so that's why it doesn't bother about all the grammars of the result, that is the left recursion or something like this, right? So that's why here is C is correct, P is false and Q is true. Q is true and P is false. Only this is the definition, right? In 2007 we got this question. So it is only two statements here given. That's why you concentrate more on the basics, not on the problems. That is the problems and thing. So basic. Suppose when you get the basic, easy you can solve the problems also. So that is the same options that you see. So second, a canonical set of items is given below. So S tends to L dot greater than R, Q tends to R dot, and symbol input less than set as. Here is the canonical items, right? Canonical item sets. I have drawn by using the some transition diagram, right? For calculation of the state S0, S1, S2, or suppose I1, I0, I1, I1, I2. So there you are using the dot production. You see that S tends to dot L and S tends to this. One input symbol less than as set as. What will I mean? A shift to reduce conflict and reduce conflicts is occur. Second one, a shift to reduce conflicts but not a reduce conflict. A reduce conflicts but not a shift to reduce conflicts. And neither shift to reduce nor reduce conflicts. You see that? So which of the following is correct? So here is we are using canonical item set of CLR. LR parcel, CLR parcel both are same. Only it will take the look ahead function and it uses the follows. But there is no time to explain all those things. But only these are the facts. Suppose here is a question asked whether the symbol S which is not present in the given canonical set of items. Hence it is neither shift to reduce conflict nor this. Suppose when you see that, suppose here is when you are taking that in canonical set of items is given. So in the grammar we are given greater than symbol. In the grammar we are given greater than symbol. But in the output symbol we are asking less than. We are asking less than. That's why answer is D. Then answer is D. That means greater than symbol is not, so that is the less than symbol is not included in the grammar. You see that? Suppose if here is the mention here is the greater than symbol, then what will happen? So then, but the question would ask like this, suppose then it would be shift to reduce conflict. Generally we can use shift to reduce conflict. Suppose if you ask this one is the greater than, here is you can get the shift to reduce conflict, or less than means the symbol is not included in this, that's why it is not added to this. So for this question, answer is D, neither a shift to reduce nor a reduce conflict. So question number 3, which of the following is true? Which of the following is true? Canonical LR parser is LR1 parser with a single look at terminal. Second one is all LRs of K parsers with K greater than 1 can be transformed into LR of 1 parsers. LR1 of parsers. So which one is the correct? The canonical LR parser is LR1 parser. Is LR1 parser with look at terminal. So that is in the beginning session I have shown that what LR parser, SLR, LR parser is a LR0 parser is a subset of SLR parser, SLR parser is a subset of LALR parser, LALR parser is a subset of, so that is the LR1 parser, that is the canonical CLR or canonical, that means CLR or LR1 parser. So that means canonical parser is a LR1 parser with a single look at table, that A is correct. All LR of K parsers with the K greater than 1 can be transformed into LR of 1 parser. That means here is LR of K means that is here is, so this is the superset of that LR parser, LR1 parser, then that's why C is correct. Both A and B are correct. So that is the both A and B are correct. So that's why answer is C for the third question. And the fourth question. Construction of canonical collection of the sets of LR1 items are similar to the construction of canonical collection of the sets of LR0 items. Which is an exception? Which is an exception? The fourth question, which is an exception? That is a construction of canonical collection of the sets of LR1 parser items are similar to the construction of canonical collection of set of LR0 items, which is an exception. But actually, so CLR is not explained, but I will explain this later. So the closure and go-to operations work a little bit different. But when you are taking the CLR canonical CLR parsers and LR0 parsers, so there is a difference, that is a somewhat different in the closure and go-to operations. Here is a go-to, that is answer is A. Closure and go-to operations work similarly. Closure and additive operations work a little bit different. Closure and associative operations work a little bit different. So that is the closure and go-to operations we are using. So additive operations, associative operators we are not using. So that's why closure and go-to operations are work with a bit difference. So in the LR0 and LR1, only that is the difference. In the next class, I will explain the difference, what is the difference, right? When B in the LR1 item, A tends to B dot A comma A is not an empty look ahead, is not an empty look ahead. What is the process of that? That is where B, so in LR1 parser, that is LR1 is not LR1, is not empty, the look ahead table will be, so taken the fifth question is, that is the B. We taken answer is, it does not have any effect. So that means, so that is we can understand this question after explaining that CLR1 parsers, right? And sixth question is the answer. So that is when, so that is the same question, I think same question has been repeated, right? Not repeated, that is look at. So that is when B is empty, there is no empty, dot of this one, dot of this comma A. The reduction by A is done in if next symbol is terminal, only if the next input symbol is A, only if the next input symbol is A, only if the next input symbol is A. So that means here is that will be reduced if the next input symbol is A. So there is a later I will explain. I will go in depth at CLR parsers in the, so the tomorrow's class I will explain LALR parsers and CLR parsers. So that I will complete the, so that is the syntax analyzer. So next in the next session I will go to, so after that next semantic analysis. That is also very important. So because, so that is also very important. You can get the more number of questions from these three. Why? Because so suppose these are the front ends, right? From the front end only we are getting more questions. From the back end sets also we can get code elimination like this. This is a very very important subject, right? So that is the thank you for this one. But here is you see that. So in this class, what we have studied. So that is what we are going to do. So simply I will explain that. So that is. So that is the main contents. Briefly, I will explain because at the beginning most of the students were absent. I have seen that, right? So that's why you see that. So the first one is we are using bottom up process. That means bottom up means the tree is constructed from bottom to top, and the next here is so important topics. That is the one is the stack we are using. So then in the parts table, construction of parts table we have studied. So that will be back in action table, and the next another one is so that is a go to table. But here is handle is a very very important. So shift reduction is also very very important. So that is the actions, table actions. That is the action table. The four actions are very very important. Or the next one is suppose is the augmented grammar. Augmented grammar. So next that is the augmented item closures. These are very very important, right? But simply just you go through the slides. So suppose everything I provided in the slides with animation, right? So then suppose when you go through my slides, definitely, so there may be chances to answer almost all questions in the gate of compiler designs, right? So thank you, and thank you for thanks for your patience. And about this lecture, suppose if there is anything, just give your opinion, right? The likes or the dislikes or anything. Either so that is how depth this class is, and that is either it is sufficient or not. Because in LR0 parsers, so I explained 7 gate problems, and in SLR parsers I explained 6. But in each and every class on the topic. That means I am doing more work for that, right? So then you concentrate on that so that it is this one, right? So thank you. So thank you for your patience. Thank you. If you have any doubts or any queries, so they can you can post the queries, or otherwise you can call me. So that is I had also given my phone number on this one. Feel free like your parent, and then you can you can ask the doubts. So thank you, and good evening to all of you. Thank you. Hello, hello. Okay, sir. Close చేసేసాయి.